This is C4 in 10 minutes. So this is a very quick review of C4 just to highlight some of the key points. So first of all, you're expected to know what each of these keywords means. So an atom is the simplest particle involved in a chemical reaction. A molecule is two or more atoms. An element is a substance only containing one type of atom. So for example, oxygen, that would be a molecule because it's two atoms, but they're both oxygen, so it would be an element. A compound, however, is a substance containing two or more different elements. So for example, water would be an example of a compound. So the atom then has several key features: a nucleus in the centre and shells around the outside. In the nucleus there are two particles, the neutron and the proton, and in the shells there is the electron. Now protons, remember the P is for positive because it has a positive charge. Neutrons are neutral, they have a zero charge, and electrons are negative, so they have a -1 charge. The protons and neutrons both have a relative mass of 1 because they're approximately the same size. Electron in comparison is about 2,000 times smaller. An atom is very small, it's got a radius of 10 to the -10 meters, and it's got a very small mass of 10 to the -23 grams. The development of the atom, there were a couple of key people involved in this. The first was Democritus, who was the Greek that proposed the idea of uncuttable particles, which he called atmos, which are atoms. John Dalton then brought the idea back about 2,000 years later and said that you could get different types of atoms, and that was what elements were, and if you got combinations of these then you got compounds. Then a couple of years later, J.J. Thomson discovered the electron, which is really important because now you've gone from the idea of atoms as sort of simple spheres that can't be broken down anymore into actually having an internal structure. So J.J. Thomson believed in a model called the plum pudding model, which is that you've got a cloud of positive charge with the electrons that he discovered being like negative plums embedded into that. The next important person was Rutherford, and Rutherford basically took this idea further and said, well, the plum pudding model is wrong, and that we've got the structure of the atom that you saw on the previous slide with the nucleus in the centre and then the electrons around the outside and everything in between just being empty space. So this is his nuclear model of an atom, which he did during the gold leaf experiment, which is worth researching. And then Niels Bohr, he came up with the idea that the electrons aren't just randomly floating around the nucleus, but they are in fact in shells, and he did work on quantum physics. So relating this to the periodic table then, when you look at the periodic table you'll see two numbers. Now the number at the bottom is called the atomic number, and that is the number of protons. Now because the number of protons must always equal the number of electrons in an atom, this number is the same. So carbon has 6 protons, it also has 6 electrons. Now the number at the top is called the mass number, or sometimes called the relative atomic mass. You'll see that notation used in C3. Mass number is protons plus neutrons. So if I want to work out the number of neutrons, I have to do the top number, take away the bottom number. So in this case, the number of neutrons would be 6 neutrons. Now, I can get substances that are the same element. So for example, these are all going to be carbon, but they've got a different mass overall. So carbon has always got 6 protons. That's what makes it carbon. If I change the number of protons, I've got a different element. So I can get carbon 12, I can also get carbon 13, and I can get carbon 14. Now the thing that's changed here is the number of protons. It remains the same, but the number of neutrons is the thing that's changing. This means that the mass of the isotope is different. So I've got the same number of protons, same atomic number at the bottom, but different numbers of neutrons, and we call those isotopes. Another example would be hydrogen. So hydrogen has no neutrons, but if I add a neutron to this, I've got an isotope of hydrogen, which we call deuterium, and if I add another one, I've got another isotope called tritium. The other important isotope that's important to realise is if you look at the mass number of chlorine on the periodic table, you'll see the atomic number is 17, but you'll see that the mass number is 35.5, and that's because that is an average taken from the two isotopes of chlorine, which are chlorine 35 and chlorine 37. So, electron configuration. Electrons don't just randomly orientate themselves, they are arranged in shells. and they always fill the lowest shell up first. So in your exams you can be asked to go up to the 4th shell because you're only going to deal with the first 20 elements. So the first shell can hold a maximum of 2 electrons. After that, each shell can hold a maximum of 8 electrons. So for example, if I looked at beryllium on the periodic table, I would see 4 at the bottom. Sorry, that'd be the atomic number, and I'd probably see 9 as the mass number. So this tells me that beryllium has got 4 electrons. So 2 can go into the first shell, and then 2 have to go into the shell that follows that. So this shows the first 10 electron configurations that you're expected to know, and this shows the next 10. You're also expected to be able to draw them. So this is them drawn out using dots as opposed to crosses, and you can see them underneath. You might need to pause this screen and have a look at that. So why is this important? Well, the group 8 elements called the noble gases, the thing they have in common is they've all got a full outer shell, and that's why they don't react. So when elements do react, they basically want to gain a full outer shell. Now there's a couple of ways they can do this. They can gain or lose electrons, or they can share electrons so that they've effectively got a full outer shell. And so that's what we're going to look at next. So an ion is a charged particle that is an atom that has gained or lost electrons. Now, because it's charged, we get an electrostatic interaction between positive ions and negative ions, and this attraction is really strong, and we call this ionic bonding. Now, ionic bonding always happens between a metal and a non-metal. If I've got just metals, then I'll get metallic bonding, which we'll talk about later, and if I've got just non-metals or 2 non-metals, I'll get covalent bonding. So, as an example, if I look at sodium, which is a metal, what will happen when I bond this to, say, chlorine, for example, is it's got 1 electron in its outer shell. Now, it wants to form a full outer shell, so it's easier for it to lose that 1 electron rather than try and gain 7 others. So, it loses this 1 electron, and it will form, because it's now got 1 less electron, but it's still got 11 protons, it will form a +1 ion. And you can see it's dropped down its configuration to neon, the same as neon would have, so 2, 8, but it's lost an electron, so it's formed a +1 ion. So any atom that loses electrons will form a positive ion because there'll be an excess of protons to electrons, and so it will be positive. So +1 ions have lost 1 electron, +2, 2, and 3, etc. Any atom that gains electrons is gaining negative charge, so it will form a negative ion. So -1 have gained 1 electron, -2 have gained 2, and so on. So as an example, if I then bond 2 materials together, I can do their ionic bonding. So if we look in the periodic table, lithium will have 3 as the number at the bottom, and fluorine will have 9. So that means it's got 3 electrons in its outer shell. So it'll have an electron configuration of 2, 1. And fluorine has got will have 2 in its inner shell and then 7 in its outer shell. So what's going to happen is fluorine's on the left of the periodic table and is a metal, so it will always lose electrons, so it's going to lose that one. Fluorine, you can see it's only got to add 1 to get to 8. So what it will do is the lithium will lose this electron and will form a structure like this, and fluorine will gain that electron. It will come from here down to there and will bond to the fluorine. So when we finish with this, how you should draw it is basically just remove the outer electron for a metal and put it in square brackets and then put +1 in the corner. And for fluorine, because it's a non-metal, you basically just add the additional electron to the structure and put it in square brackets and put -1. Now an important thing that is wrong about this diagram is that it's all been done with crosses, and what you want to do is you want to use one diagram, you want to use dots, and the other you want to use crosses. And the reason for this is so that you can track where the electrons have come from. So if I just correct this lithium by changing these to dots, what that means is that when I do my fluorine over here, this 1 electron has come from the lithium to the fluorine, and so I can draw that one as a dot, and so I can see exactly where that has come from. Magnesium oxide would be another example. Again, the same mistake is made here, that crosses are used in both diagrams, but again, you should put it in the square brackets. Now magnesium, because it's in group 2, will lose 2 electrons, because it's got 2 electrons in the outer shell, and so will form a +2 ion. Oxygen is in group 6, so it's only got 6 electrons in its outer shell, so it needs to gain 2 more, so it would be that one and it would be that one, and then it would again have square brackets and form a -2 ion. Now, ionic compounds formed by these charged particles form giant ionic lattices, which you can see here. This is sodium chloride and this is magnesium oxide. These are the two you need to know about. So this is the giant ionic lattice, this is their structure, and that determines a lot of their properties. So you can imagine that these are the positive sodium ions and these are the negative chloride ions, and the attraction between them is what's holding this lattice together. So the ionic charges on these, well, if we compare sodium chloride, which has got sodium, which is in group 1, so it forms a +1 ion, and chlorine, which is in group 7, so it forms a -1 ion. As you can see here, it's got a melting point and boiling point. It's pretty high, but if I increase the charge, because magnesium is in group 2, it forms a +2 ion, and oxygen's in group 6, so it forms a -2 ion. You can see this has a massive impact on their melting point and boiling point. So generally speaking, because ionic bonds are very strong, ionic compounds have a high melting point and boiling point, okay, because of the strong ionic bonds, and the stronger the bonds, the stronger the attraction, and so hence the higher the boiling point. They also tend to be brittle, so when I put a force on them they will break apart, and the reason for this is because of the repulsion between the ions when they pass over each other, so they often are very brittle. As a solid, it won't conduct electricity because there are no free electrons, but if I melt this down to a molten state, so I either heat it up and melt it, or I put it into a solution and make it soluble, then it will carry an electric current, because now I can get free ions, so the ions are free to move, and so it will carry electricity. And they also form a crystalline structure. So there's a couple of other ions other than straightforward ions that we need to be aware of, which are called polyatomic ions. So the hydroxide ion is an important one, which is poly means many, so polyatomic means more than one atom in an ion. So this has got oxygen and hydrogen in it, and so hydroxide is an important ion you must learn. The sulfate ion again is another example. It's got 1 sulfur atom and 4 oxygens, and overall it has a charge of -2. Nitrate is NO3-, carbonate is CO3-2, and the ammonium ion is the only positive one that you need to remember, which is NH4+. I'll just point out that if it says 8 at the end, then 8 means with oxygen, so you can see that all 3 of these have got oxygen in them. You'll learn about each of these at different points in your course. Okay, so covalent bonding then. So the other type of bonding that we need to talk about is covalent, and in covalent bonding what happens is we've got a shared pair of electrons. So for example, if I look at a non-metal like chlorine, I would see on the periodic table, if I was to look at chlorine, that its proton number or atomic number would be 17. So that means it'll have 2 electrons in its first shell, it will have 8 in its next shell, and then it will have 7. So to get to a full outer shell, it needs to add 1 more. Now, rather than gaining an electron from somewhere like an iron, which it can do, if it's bonding with another non-metal, instead what it will do is it will share an electron. So these 2 chlorine atoms, if I was forming a molecule of Cl2, they will bond together and they will share this pair of electrons, which we call a covalent bond, and we represent that as a single line. I can get single covalent bonds, I can also get double covalent bonds and triple covalent bonds. Now the structure of covalent compounds is such that we've got the molecules which have strong covalent bonds in them, and then we have weak intermolecular forces between the molecules, and that is a key word that you need to be familiar with. It comes up, is used a lot in C1 as well, so weak intermolecular forces, and that means that overall they tend to have very low melting points and boiling points, so most commonly they're gases at room temperature. That then moves us into group 1, which will be the starting point for our next short video.